Hello and welcome to our fifth and final lecture regarding aortic stenosis. With this lecture here, we're going to learn about the principles of peak pressure gradients, explore mean pressure gradients as a way of measuring valvular stenosis, learn some of the reference ranges for each method, and then review the differences between catheter-derived pressures and those obtained with echo. Pressure gradients are worked through with the Bernoulli Equation. A change in pressure is equal to the sum of convection acceleration, flow acceleration, and viscous friction. Now, fortunately, this very complex formula can actually be simplified. We're investigating peak flows. Thus, acceleration is effectively non-existent at peak. Blood velocity and blood viscosity influence viscous friction, and these play a negligible effect when the orifice is greater than 0.25 centimeters squared. And that's pretty much everything cardiac. So that can also be ignored. So that just leaves us with convective acceleration, this component here. And so we have a much more manageable calculation. Now, when you consider the density of blood, the calculation is displayed as what we see here. And in many instances, for cardiac imaging, V1 is minimal in velocity, normally less than 1 meter per second, and plays a negligible effect when V2 is large. Such as if you consider 64 minus 1 bears little significance to the end result. So a calculation can be further simplified to 4V squared. It is important to note that this does not define the pressure itself, but the pressure gradient as stated between two chambers of the heart. An example may be necessary where it's important to include V1. This would be, say, in the aorta in the presence of coarctation. The velocity of V1 may be easily higher than 1 meters per second, and the coarctation itself could be mild. Thus, by excluding V1, the pressure gradient is significantly overestimated. Another example may be blood leaving the heart and into the aorta. Blood through the LVOT may be significant in relation to the aortic valve flow. And in this example that we have here on the screen, if we had an aortic valve flow 3 meters per second and LVO2 flow was 2 meters per second, we would have a corrected velocity of 20 millimeters of mercury. But if we excluded V1, we'd actually end up with 36. So 45% error if it had not been included. Pressure gradients are also a useful tool in the determining of valvular stenosis. Basically, the higher the gradient, the greater the level of stenosis. Care, however, has to be given if there is anemia, polycythemia, outflow tract extraction, significant aortic regurgitation, or an increased, decreased cardiac output state. These will significantly impact the obtained results, so it's good practice to not use this value in isolation when determining stenosis. But we can see from our charts here, if we had a velocity that was in the range of around about 4 meters per second, it would come in the moderate area. And we could work out our 4V squared to also see that the change in pressure there would sit in that range also. Care must also be given in small LV cavities. The small LV cavity leads to a small forward stroke volume through the valve, and thus low pressure gradients. Typically, a patient with small cavities have increased heart rates to maintain an adequate cardiac output. Conversely, if the patient demonstrates a hyperdynamic systolic function, the gradients seen through the valve are higher than one would expect. The continuity equation is not affected with significant LV dysfunction. Stroke volume through the aortic valve and the LVOT are both increased or both decreased, so the overall effect is negligible. We must also consider the effect of significant mitral regurgitation and how that can play on aortic gradients. Flow will always take the path of least resistance. Since flow will readily move from the left ventricle into the left atrium with its relatively lower pressure, Less blood was then driven forward through the aortic valve, and thus we obtain lower pressure gradients. The mean pressure gradient is another useful tool used in echo. This assesses all the velocities over the duration of the flow. We obtain a mean or average velocity, and this is represented here. Fortunately, the machine does this calculation for us, as all we need to actually do is a tracing around the flow profile itself. There is also a simplified gradient calculation that may be applied to a native aortic valve just by taking a maximum pressure gradient. Working through the formula, we can just come down to 2.4 V squared. We'll work out the mean pressure gradient. And looking at typical values that we'd have for mean pressure gradients, if we had a mean pressure gradient of less than 25 millimeters of mercury, then we're assuming that we've really got mild aortic stenosis. The proximal isovelocity surface area is another method we may deploy to evaluate aortic stenosis. It's based on the principle of the conservation of mass. This calculation makes the assumption that flow moving through a regurgitant orifice is equal to flow within a hemisphere that forms as flow converges as it progresses towards the valve. Basically, a radius is measured from the valve leaflets out to a hemisphere, and we know a hemisphere area to actually be 2 pi r squared. From the apical view, a sonographer zooms on the valve and applies color. The baseline is moved in the direction of the flow. Because we know the aortic stenosis flow is moving downwards away, then the baseline is moved downwards also. The distance from the orifice to the first aliasing velocity is measured, and the aliasing velocity at this point noted. Then continuous wave Doppler is placed through the valve from the most appropriate window that gives the best flow alignment. As with the continuity equation, we know that a volume of blood, in this case with inside a hemisphere, will be the same volume of blood that actually moves through a narrowed orifice. So we come through with our equation, the effective orifice area is equal to 2 pi r squared times the aliasing velocity divided by the velocity through the stenotic lesion. This is all fine except for the fact that the leaflets are semilunar and that the leaflets are often not flat in systole. A funnel shape may be made by the leaflets or a domed appearance, particularly with bicuspid and rheumatic valves. To measure the radius from the leaflet orifice and place a dome over the top makes the assumption of a formed hemisphere incorrect. The actual area within this will be less. Therefore, PISA is used as a guide rather than an absolute value when assessing aortic stenosis. For those working in the catheter laboratory and those in the echo clinic, they may see the discrepancies in a patient with a catheter and echo-derived pressure gradients for aortic stenosis. This is also related to the pressure recovery concept detailed earlier. In the cath lab, the cardiologist pulls the wire from the ventricle into the aorta. What is recorded are two separate measurements, peak aortic and peak left ventricular gradients. This peak-to-peak method values simply a derivation of the largest gradient of the LV minus the lower one of the aortic. This is a non-physiological measurement as the readings cannot actually be made simultaneously. Reviewing the pressure waveforms we'll see on the next screen, we can see the aortic peak pressure occurs after the LV. And this is because the LV needs to generate significant pressure to force blood through the narrowed orifice and actually open up the aortic valve. In echo, the Doppler measurements of a peak gradient are instantaneous of a change between the left ventricle and the aorta. And again, when we review the pressure gradients on the next screen, we'll see the gradients obtained by echo will be much higher than by catheter. However, what does correlate very well between echo and catheter readings is the mean pressure gradient. So we can see here a peak-to-peak obtained by catheter-derived method, and that they're non-simultaneous peaks. And if we do a peak to peak with echo, we'd get a much higher gradient as we'd see here. If we were to do a mean gradient, we measure the velocities within this area here by echo, and that correlates relatively well with what we actually get with catheter work. When we work with catheters, we also can use the Bernoulli equation that simply has the formula that aortic valve area is equal to the stroke volume divided by the systolic ejection period, divided again by a constant of 44.3 times by a square root of the change in pressure. It's important to note the fixed relationship. So if we know the aortic valve area is fixed and the stroke volume goes up, the change in pressure must correspondingly also go up to keep everything constant. And therefore the other way. So stroke volume goes down, then this change in pressure must also go down. In summary, peak and mean pressure gradients assist with the assessment of stenotic valve lesions, and particularly with the aortic valve. Basically, the more methods we apply, the greater the confidence we have in the investigation actually being performed on the aortic valve. The Bernoulli equation can be modified to a simplified form, but with these simplifications come limitations, along with those already existing with the Bernoulli equation itself. The PISA method has limited application, however, they may be used as a guide with aortic stenosis assessment. And discrepancies exist between catheter-derived aortic measurements and those with echo gradients. But we must always consider that cath work is the gold standard.